All right, here are the slides, and here's me. Hello, welcome to my talk about compiler backdooring for beginners. My name is Marion Marschalek. I'm a security researcher at heart. I currently sport the title Senior Cloud Security Engineer. I work for a large cloud provider, and that is also why I will start out the presentation with a disclaimer that I do not speak for my employer, and opinions here expressed are only my own. Who am I? I'm a reverse engineer by training. I love binaries and everything you can do with binaries. And I found my love for compilers a few years ago when I was working at Intel. I was working on a team that was researching CPU vulnerabilities. And at the time, I didn't understand much about CPU vulnerabilities or about compilers. And one day my manager walks in and asks me whether I want to learn compilers because they had interest in prototyping mitigations to test those on certain software packages. And so I had this opportunity to spend my time at Intel studying GCC at the time, trying to build compiler mitigations to test those in certain pieces of software. And I'm telling you, learning GCC is hard work because GCC virtually doesn't have documentation to write software that works with GCC, which I learned the hard way back then. So if you start working with GCC, you're essentially trying to piece together the first Hello World. It took me 2.5 weeks to get a Hello World as a GCC plugin going. And in comparison to that with LLVM, it takes 5 minutes because you just download the thing, compile it, and it runs. And that was a very different experience. For this presentation today, I was focusing on LLVM and Clang because initially this project was meant to be a training. I still have the plan to take the material I have and make this an introductory training. Next to being a security researcher, I also am a trainer. I teach reverse engineering classes. As you heard in the introduction that Samir gave us, I teach free reverse engineering classes for women to motivate them to move into the reverse engineering field. And I also want to motivate them to move into the compiler field because it's just as much fun as reverse engineering. Now though, I said all this. Why? Why are we here today? And this, by the way, might be my favorite slide in the slide deck. Again, I'm here today because of the love for compilers that I found a couple of years ago at Intel. And I want to help people understand this field of research and find more folks who want to dig into this subject. I understand that GCC is not the most approachable compiler. However, LLVM is. And something that I found out preparing for this presentation was rather sobering. I wanted to do my backdooring research in LLVM, and I was actually more successful at that than I thought. So I started building a backdoor, and I had the code running, and it worked, and the backdoor worked, and the proof of concept was basically done. And by the time that worked, I still didn't understand how Clang works, because it didn't even need to go and read the documentation. However, today I want to present you the things that help you get going just like I did. That is also a disclaimer. I'm not a specialist in LLVM. I'm not even a specialist on GCC. I'm a security researcher who found the interest in compilers and approached those subjects from a security research mindset. And of course, if I work on a compiler, what else would I do than try to place backdoors? But I wasn't the person who first had this idea. If you look up compiler backdooring, you will find a very famous lecture that a person named Ken Thompson gave in 1984 when he received his Turing Award. It is titled Reflections on Trusting Trust. And what Ken Thompson did at the time was he modified a compiler to plant a backdoor in a binary that's located under /bin/login. And I actually checked, the current Unix systems still have this binary. It is used during the login of a user. If you put a backdoor in there, every time a user logs in, a backdoor will be opened. And we will see in a couple minutes how such a backdoor could look like. What Ken Thompson also did, however, was he backdoored the compiler he used for compiling, for backdooring that login binary, which is extra nifty. What he tried to demonstrate was that we're trusting binaries that we don't know where they're coming from. and we all do this. Something you realize when you think about the subject is that compilers are underneath everything we do today. Like you use your phone, you use your computer, your mom uses her phone. All of the software that's running on there is built by a compiler. And implicitly, we have to start trusting somewhere because compilers are built, you guessed it, by compilers. So if you have a compiler that's also been built at some point, who tells you that there's not a backdoor that's been put into that compiler? And I'll also tell you, I don't want to cause unnecessary fear, like we're already scared enough in the security industry. I don't think that compilers are actually backdoored, and I don't think that people like maliciously will do that, but there is a possibility. And currently we don't have a good way to check for those type of attacks. A more recent event that shows us how quote-unquote helpless we are in those situations is an incident that everybody will have heard of, the SolarWinds compromise, where attackers compromised the build system of the SolarWinds software build chain, and they placed malicious code into their software update. So then SolarWinds was rolling out a backdoored update to approximately 18,000 customers, which you will know if you read the Wired article that I linked on the slide. That's a very nice introduction to that type of attack. And as you can see on the slide, one of the investigators called it sheer elegance. It was a very nifty attack. It was very tricky, but I noticed that even in this attack, people didn't attack the compiler. They placed extra code in the build system and then trusted the regular compiler to put that code into the update to ship the backdoor. They didn't touch the compiler. And it's interesting, if you look at actual in the wild attacks, I didn't find any indicator of compiler backdooring or like placing backdoors through compilers having happened in the wild, which surprises me because especially with LLVM, it's not a very unapproachable subject. Which brings me to a conundrum. As the world starts adopting LLVM more and more, compiler attacks like the ones I will show today become much more approachable. Because again, like for building the backdoor that I'll show you guys, that took me like maybe half a day, maybe a day to get this going and set up the proof of concept, which is very approachable for an attacker. So implicitly, there is some security by obscurity if your build chain is using GCC, because again, approaching GCC is so much harder. And I'll explain more throughout the presentation of why that is the case. All right, enough talking. Let's start with the backdoors. And by the way, I very much appreciate the LLVM logo. Like GCC has this weird GNU that's kind of coming out of a corner, and LLVM has this really cool dragon. And who doesn't like dragons, right? All right, then let's take another second and do a prayer to the demo gods. Because I'm absolutely not sure this is going to work. Okay. So, first of all, that's the wrong terminal. Right terminal. AVR, we have connection. Awesome. What I'm going to do here is I'm going to start a listener. I'm going to start a program called Net. Can you guys see that actually? Okay. The people in the back might need to squint. Can I go a bit bigger? That's bigger. So I'm starting a tool. It's called Netcat, which is a famous penetration testing tool. It's famously used for backdooring or listening to backdoors. And what I'm doing here is I'm simply starting a listener. So Netcat will start up and it will start listening on the port 8080, which is what it's doing now. It's telling us it's listening. So this is my attacker machine that I'm on. And I'm switching to a different terminal. This is our victim. If you see in here, I have two projects, Nginx and PHP are the two folders, and those are the two proof of concepts I wanted to show today. And the other folder here is the LLVM project. For the demos here, I built my own LLVM, which is actually the recommended way to approach LLVM. Like you clone your own repo and you build your own projects, which is where you find the first challenge of digging through the documentation, finding all the arguments you need to actually build the right LLVM and have all the right tools available. But that's a whole different story. One hang-up that I will talk about towards the end of the presentation is that any code that you build to run with LLVM needs to be built with exactly the LLVM version that it's supposed to run with. That's why I have my own clone of LLVM on this computer. Now, the first demo that I wanted to show will be Nginx. Okay, go in this folder. There is a folder that's called inject. That is my plugin. By the way, I built the backdoors as plugins for this presentation because it's so much easier to use than modding the actual compiler. But I have a slide about modding the actual compiler as well. If you want to do a proper backdoor that's really well hidden, you would put the backdoor in the compiler code itself, and that comes with its own issues. And I have a slide about that later as well. Now, what I wanted to show you is we have this, we have a plugin in inject, and that has been used to build Nginx. By the way, I will not compile anything on stage today because that would be very boring and we would watch the compilation process for the next 20 minutes. So we're not doing this. I pre-built everything and I'm just running it, and you just need to trust me that I built this myself. Okay? So let's just go straight in here and in the opt folder. This is where the output binary sits. Here you see Nginx. This is what we're going to run. And we're going to run this with sudo. And now we're going to hope for the best. So as I start this, give me a terminal, dum-dum-dum, and oh, here we are. It worked. Y'all are applauding. You don't know yet actually what happened. So I started the Nginx binary in the other folder, and I put a literal backdoor in there, a backdoor code. So like there's a shell command in that binary that will pop a reverse shell and connect to this other machine. And now that I'm here, I'm in the object folder of Nginx, and I can listen, I can list the directory, and I can see which user I am. I'm actually root, because like if you saw, I started Nginx with sudo. And so if you started with sudo, you also execute the reverse shell with sudo, and then you connect back to the machine and your root, which is like, boom, sweet. Cool, so that was the first backdoor. Now, let me actually explain to you what just happened. That is the point of the rest of the presentation. Let's jump back into the slides, full screen. Yeah, so, that was exciting. We had a backdoor. That worked out. Now, let's look at what actually happened. First of all, whenever you see anybody talking about compilers, they have to have a slide like this that shows you the high-level 1 million foot view, and you will see that everywhere. And if you Google LLVM and GCC, like, you will get this same picture, which shows you that the compiler has front end, a middle end, and the back end. And every introductory blog, etc., also has the same structure, and that is very surprising how many introductions to LLVM stop at that explanation, which is very useless. However, I still decided to have the slide in here, so we have a front end, a middle end, and the back end. The front end for LLVM that most people will know is Clang. Clang is the C and C++ front end for LLVM. That will take your C code and will produce something out of it that we'll be talking about in a second, and lower that to an intermediate representation, which then goes to the middle end. The middle end is what most people understand as LLVM. So when we talk about LLVM, we talk about an infrastructure of different tools, but what we mostly refer to with LLVM is that middle end component, that is the optimizers. The optimizers are organized in the pipeline. I'll be talking about that as well. And something that we won't be touching in this presentation is the back end. Imagine you have your source code that is transformed into intermediate representation, and that intermediate representation then in the back end is lowered into the actual machine instructions. And that could be any architecture. So essentially what that framework wants to do is do any given source code, take any given source code like C or Go or Rust, have that be taken in by the respective front end, lowered into the same intermediate representation. And from there, you can transform it into any given CPU architecture like x86 or ARM or whichever one you desire. You understand, but LLVM you can literally build for all of those different architectures. Awesome. Now we saw the 1 million foot view. Let's go a little deeper. As mentioned, LLVM is a compiler infrastructure. That is a very nice word to say it's a bunch of tools that all usually sit in the same folder and have a lot of different functionalities. And it comes with an overwhelming amount of documentation, which is both very good and very bad. Also, as just mentioned, Clang is the front end for that compiler infrastructure. the main job of Clang, like any front end in that respect, is to produce an abstract syntax tree. We also call it the AST. The AST is a tree, as the word says, and it is rather confusing. It is meant to be understood by the compiler, not necessarily by humans. But we're going to see that on the next slide as well, how that looks like. And then important, you will hear the word passes a lot in this presentation. Compilers are organized in passes. So like you handed a representation of first the code that is changed into an abstract syntax tree, and then that is changed into LLVM IR, and then you run an optimizer, and another optimizer, and another optimizer. These theoretically run one after another, but of course compilers are complex and complicated, and so it's not necessarily the case that one pass runs after another pass. So like if you list the passes, you get a nice list, but sometimes those passes depend on each other, especially if you have analysis passes and transformer passes. Sometimes a pass depends on the output of a different pass. So then those have to run in order. And as such, people came up with the concept of different pipelines. And we won't go into details there. Neither could I tell you the details about this because these optimizing pipelines are probably the most complex part of any given compiler. What you see on the screen, by the way, which I found very interesting, the graphic that I used for decoration around here is the printout that you get if you tell Clang to please tell you all the passes that are ran for a given compilation job. So here I ran Clang with the optimizer O2 on a simple hello world printf, and with the option debug pass equals structure, you get all the passes that LLVM will run on this one project, like in this job, which is very interesting to see if you use different optimization settings, which passes are actually applied to your code. So that's helpful. Then I promised you an AST, and this is about as much as we're going to see of an AST today. But here on the slide, you can see the actual abstract syntax tree of a printf hello world. There's a big stack of nodes on top that belong to library code, but then if you look at the bottom, there's something that's called compound statement. It's tiny little down here. It says compound statement. That is the whole printf hello world statement. And then there you see a call expression, which is the printf, and that contains a string literal, which is the hello world. Okay, so this is Clang land. This is what Clang works on. If you modify anything in Clang, you will be working with the AST. And that is not what I did, so this is as much as we're going to hear about the AST today. Let's move on to more interesting spheres. Let's look at the intermediate representation of LLVM. Intermediate representations are interesting magical creatures that look a lot like a mix of C and assembly code. And on occasion they can be confusing. LLVM's intermediate representation is built like a 3-address format, also called static signal assignment, which basically means that an expression that might be a complex C statement, or like a complex statement in C, as you see in this example on the left side, with like x equals something, something, square root, etc. That long statement can't be represented as it is in assembly. You'll understand that if you see in assembly, like, you have like an add instruction and the multiply instruction and the move instruction, but you can't do like this whole statement in one instruction, or like in a few instructions. So essentially how this lowering process works is the intermediate representation tries to take those long statements and split them up into like digestible little chunks. And the point of the 3-address format is that we have a receiving variable. As you see in the example here, we have T1, T2, T3, T4, etc. And on the other side of that needs to be either 1 or 2 items. That's what I refer to as a 3-address format. And by splitting these statements up into these simple steps, that makes it easier to A, run optimizations on the code, and to B, lower this representation to the assembly representation. I say representation a lot today, it's weird. Also, I've been speaking all day. If my voice keeps failing me, that's because I've been speaking all day. Okay, this is as much theory as we need about the IR. Now, how does it look like in practice? It is, as mentioned, a very interesting magical creature. Actually, looking at the LLVM IR, I was a little bit disappointed because I think GCC has the cooler intermediate representations. If you want to see something funky, look at the GCC RTL representation. That is like writing assembly with a Lisp accent or something like that. It is both beautiful and horrible. However, in the LLVM, we have this intermediate representation that looks a little bit like assembly. Important here is that we have an endless supply of variables and we have an endless supply of registers. What you see on the screen is the LLVM IR of a function that I've typed into Compiler Explorer. How many people in the room have ever used Compiler Explorer? Your hands go up. Cool. And the rest has no idea what I'm talking about. Compiler Explorer is a website. You find it under godbolt.org. Godbolt is the guy who came up with that system. There you can explore how compilers work. It is rather fascinating. So you type in a piece of source code and you can look at the assembly that will be generated by a given compiler for a given architecture. But you can also look at the intermediate representations of the different compilers, which I only found out recently, and that is awesome. So like in there, I don't need to run any tool. I have a website and I type in code and see the intermediate representation. That would look like this one. We could now go on a reverse engineering exercise and figure out what this code does, or I could just tell you. If you look on top of the screen, there's a string that says 4 + 6 = %d. Essentially, what this does here is we load two values, the value 4 and the value 6, into variables, and then we have a printf that prints the addition of those two variables. And if you see there's two store instructions for 4 and for 6, and then there's an add instruction down there that adds %0 and %1, which are those two values that we just saw. And then there's a printf with the format string that's not on the screen. So you see it's a little bit like assembly. If you are reverse engineered assembly, then this might look familiar. And that's exactly what this intermediate representation wants to do. You try to translate the C code into a representation that is both abstract and close to the assembly that's coming out on the other side. If you looked at different assembly languages before, they all kind of have the same mechanisms. Like they all have add instructions, they all have load and store of some form. And so compiler intermediate representations are really just an abstract form to explain, like to show any given assembly representation. And that's what makes them both so cool and so horrible. All right, this was your quick introduction to LLVM IR. Now a little bit more about LLVM. It's a collection of tools, as mentioned earlier, and it has a list of very cool tools that we also don't have the time today to go into details with, like, for instance, the LLVM optimizer, the opt tool, which essentially shows you the LLVM optimizer pipeline, and with the opt tool, you can turn on and turn off specific passes. You can also test your passes with opt. That's very cool. And the other tools are very nice as well. Also, they're all released under a very permissive Apache 2 license. If you were to modify and use those tools in any tool chain, as some of us might have done. Then something I've mentioned earlier, there's an overwhelming amount of documentation for LLVM, specifically the LLVM Programmer's Manual, which is also both wonderful and horrible, because you could spend the rest of your life reading LLVM documentation, which is great. Obviously, if you want to learn something specific, if you have a specific question, you go to the docs and you look up the solution for that. If you don't have any specific question, you just want to learn a little bit about LLVM, high level, the documentation is not the place to go. And in fact, there isn't a very good place to go to learn just a little bit about a compiler, which is a little frustrating. All right. LLVM passes and pass managers, and we're still in the theory, and I'll move a little bit faster here to save some time. Again, compilers are organized as a series of passes, and those passes kind of take the code, and it's not like a pipeline where one thing happens after the other, but it's like pipelines that happen in parallel and that interact with each other. So it's like this machinery that takes the code and kind of massages it into the final representation. As mentioned earlier, we have analysis passes and transform passes, and they sometimes depend on each other. We also have module passes and call graph passes and function passes and loop passes, and there's also basic block passes, and then there's another pass type that I forgot completely. And these are literally passes designed to tap into the pipeline where the optimizations run, and then interact with either a module or the call graph of the module, or a function, like all the functions in the module, or all the loops in the module, or all the basic blocks in the module. And I haven't explored very many different types of those. I've mostly worked with module passes, as you see when I explained the backdooring. For more screenshot of Compiler Explorer, this is the tool that I mentioned earlier, and you can literally look into the optimizer pipeline there. Like you type in the code, and there is a drop down that says add, and you can add the pipeline view. And in there on the left side, you have all these different options of where you can look at the representation of the code as it moves through the optimizer pipeline, which is really quite cool. And also, I have absolutely no idea what the slide says here. You could go and reverse engineer this specific representation of the code as it is in the stage of the prologue / epilogue insertion and frame finalization something pass. This is how it looks like. And I really just wanted to show this tool if people want to go and like dig deeper into optimization. This is where you would do that. Finally, to get started in the subject, again, there's tons of documentation. I recommend you not starting in the documentation, but start with example code. And there's tons of that as well. And 2 repos that I can highly recommend are on GitHub by user named Banak Space. Well, that means they're called LLVM Tutor and Clang Tutor. That's where most of my knowledge about LLVM passes comes from. And the other links here are highly recommended as well. All right. So now what about that backdoor? How did that happen? Let me explain that a little closer, and then we're going to get to the second demo. And the second demo is going to be much cooler, I promise. So that backdoor was produced by this plugin code. And we won't go into details about APIs here either. But if you have a quick look, you see one line that sticks out in particular, which is right there in the center that says LLVM constant data array get string. And then it says bash -c bash -i, etc. Then there's an IP address. Then there is a port, the wrong port, by the way, I just realized. So I didn't update that slide. Whoops. And then it shows that that bash process will run in the background. So that is the line of code that popped the reverse shell. And now I can understand if some of you are disappointed. This is like a really simple way to build a reverse shell. And I really just wanted to show you how easy that is. There's different issues with how I solved that specific problem, and I'll talk about this in a second. But so it doesn't take more than this piece of code. There's some glue code in there to actually get the plugin built as a plugin and to get the plugin registered in the specific pipeline where we want to run it. But I figured that this is enough source code to put in the slide already, so I'll spare you the rest of the code. So what the code does is you need to tell the module that you have to have the system function. System is what launches our reverse shell. You have to set attributes for that function, which I did there. That's, in my opinion, is rather cosmetics, but it needs it to get running. You need the string that you want to inject, which is that bash-c command that you see there. That string is the reverse shell that we're going to be putting into Nginx. Then there's a loop, and that loop looks for the main function. I literally just looked for the main function, looked for the entry point to the first basic block, which is what this get entry block API there does, and placed the system call right there. So there you will see, if you look at the disassembly, you will see system and then a link to that string, like a cross-reference to that string that will pop the backdoor. And what puts the actual call into the binary is an IR builder. With the IR builder, you can build yourself components of code that you can then inject into the code you're compiling. Cool. Now we understand all those APIs. Now, I kid you not, I don't know how those APIs in the screen do. Literally, please download the proof of concepts from GitHub and place your own commands in there and you have a backdoor. It's that easy. And about that backdoor. Yeah, it was inspired by a tutorial by a person I've never met, but I absolutely adore because he put on the LLVM tutor repository where all that code lives. His name is Andrzej Wyszynski. And apologies at this point if I spell his name wrong. And this plugin, like, he built a pass and I turned that pass into a plugin again so I can run it without recompiling the whole LLVM stack. That needs to register in a pipeline, and I specifically chose the callback register pipeline stardp callback that taps in at the beginning of the default optimization pipeline. At least that's what I read on the internet. And so when we inject there, it's essentially our call lives through the whole optimization pipeline before it's being spit out into the assembly that comes out on the other end. You also need to find the right module. If you compile Nginx, you need to find out which module you actually want to put your code in. A module in this case would be almost equivalent to a C source file. And there's a definition somewhere what LLVM thinks is a module, but in reality, it's almost always the C source file that you're compiling. And in there, we need the declaration of a system function, which you just saw in the source code. We inject the string to the reverse shell command. We iterate the functions in that module, find the main, and inject our call. That would be the documentation to that backdoor that I showed you earlier. And enough talking about source code. Let's look at some binary code because that's much more exciting. Here's the disassembly of the main function. And you see right there in the center is where we load system command, which is the string that we need for the backdoor, which is also listed in the hex thumb up there. You see B2980, that's the offset of the string that we want to reference. And then there we have a call instruction that goes to system@plt. And that call is what will launch the reverse shell. All right, that's kind of clunky. And you will recognize that I hard-coded an IP address in the backdoor. The IP address is hard-coded in the Nginx, which is kind of an issue. You know, IP addresses aren't that static. You also need to pray for a clear path to the internet, or that the firewall lets you through. I actually had an issue there. First I ran this, I forgot that my firewall blocks 8080 and I couldn't actually get the backdoor through. So if you're in the wild, then this type of attack probably will not actually work. Also, there's no relaunch strategy. Once your backdoor dies, there's no mechanism in the current code that's injected that restarts that backdoor. So once that's dead, your access to the server is effectively broken. All right, damn it. Let's do something cooler. There's so many different ways of how to do awesome things in the compiler. Like, you can add rogue code, which is what we just did, and you can do that much better than what I showed you. Like, I really showed you the simple stuff with injecting this one system call, but you can literally put an entire source file into the target with a very similar attack. Also, you can go ahead and remove security features, which gives you the challenge that you still need to find a way to abuse that lack of security features, which is a lot of work. You could introduce bugs, which comes with a similar issue. If you introduce a bug, that's great. There is a vulnerability, but now you need to exploit that vulnerability. And that brings me to the fourth point, which says remove a patch, which is my second demo. If you remove a patch that has an existing proof of concept exploit, you can exploit your target right out of the box without actually writing exploits, which is great because it saves you a lot of time. All right. Which patch did I remove? I went for a vulnerability in PHP. I actually forgot to put the CVE number on here, which is bad on my part. But you can easily look that bug up, and also the exploit that exists for it. That's on GitHub. And what's beautiful about this specific case is that the person who discovered this vulnerability not only wrote an exploit for it, he also published the exploit. He published the source code. He published a Docker repository that's vulnerable, that helps you reproduce the whole thing. And he gave a talk about it at a conference, published the slides, and one of his friends wrote a very detailed blog post about the bug and how the exploitation works. If you're interested in that subject, I can highly recommend check out the repo, watch his talk, and read that blog post that exists in the bug. It is very educational. And also, that is the reason why I will not go into details now about what the vulnerability actually is, mostly because we don't have time for that. And if you're interested, again, please check out his repository and reproduce that bug. It is very educational. Why I specifically chose that, again, like there is an exploit and the reproduction environment is there and all, but also the patch is very simple, which makes my life easy if I want to remove a patch and the patch is really just 2 lines of code. That's easier than like removing a rather complicated patch. What is the patch though? If you go patch hunting on GitHub, you find this one commit, and I posted the link on the slide that shows you that the patch, there's the CV number, CV 2019-11043. It's a remote code execution because of a buffer underflow in the PHP FPM module. And that was patched in 2019 with this simple fix where they changed 2 lines of code and they essentially added 2 checks to make sure that their buffer size can't be underflowed. And, which is a checkbot on the compiler backdooring side, because that means that we really just have to change these 2 checks. Awesome. How do we do this? For research in a bigger project like PHP, you need to get a little bit nifty in how to actually find the location where you want to remove that patch. So I went ahead and did a dirty trick there. I downloaded the source code and compiled it with markers. I put 2 printfs in the source code so that when I print out the intermediate representation, I find the location of where that patch was located at. And I am sure that there is smarter ways to do that and more elegant ways, and I didn't want to spend the time to explore them, I'll be honest. So I just put my printfs in the code, dumped the intermediate representation of LLVM, and thus found the patch location, which isn't backdooring yet. We just found the place where we need to place the backdoor. And from there, we started strategizing. How that looks like is this. In the beginning, I showed you like a very neat, nicely organized piece of LLVM IR. That's not how reality looks like. Apologies. In reality, LLVM IR looks much like this, what you see in the slide. Again, you have an endless number of variables, which is the %500 numbers you see on the left, like %535, for instance, 536, and that just keeps numbering on through the module. At the end of the module, you have like %10,326 or whatever, because that number just always grows. Because again, you have this endless amount of variables, and you also have an endless amount of registers, which here in this code you see as these % numbers. The first block I marked out, you see this inconspicuous long arrow there. That is the first check that we want to look at. I copied the patch code, like this little screenshot of the patch in here, where you see the comparison between a variable named pilen and whether that's bigger than slen. So that is a check that was put in as the patch, and that is what we want to target in the plugin. And if you look at that code, you see that pointer 30 and pointer 29 are 2 variables, and then there's a compare statement that looks for a greater than. And because I had the printfs put, and because I see the greater than and I see the 2 pointers, I know that this is the specific line of code, or the specific portion of code that I'm looking for. In the LLVM IR, I didn't find a good way to uniquely identify a given instruction. Like, imagine you look at the disassembly of this function and you like see an instruction. There's no good way to look for it necessarily. So I can't like just grab through the LLVM and find the one instruction that I want to patch. That's simply just not how it works. But I need to identify those instructions by the context that they're sitting in. So that's what I did here. That's what I have on the first statement. And for the second statement, it is similar. We're looking for a check of a variable against null. So you see path info then in the second line of the patch that needs to be positive or not null in order for this check to succeed. And we find this check a little later in the code where we have pointer 32 and pointer 32 is loaded and then lands in pointer 546, which is the instruction that happened before and that's compared with null. That is the second safety check that we want to identify. If you're not a reverse engineer, this looks like Chinese, like absolutely confusing. If you are a reverse engineer, this still looks confusing, and I understand that. I can relate. If you spend some time looking at it, though, I swear it is very easy. It is like very easy assembly because you're not limited to a certain set of registers or like a certain set of variables. So this code just goes on and on and on and does the same thing all over. All right. But so now we identified the checks that we want to remove. Now, how do we do that? Here's another piece of code. At this point, I apologize for all the C code on the slides. But so this one's actually simpler than the other one, which surprised me. This was even quicker to implement because it is rather simple. So what this plugin does, and there's code missing to this plugin again. There's like the registration of the plugin, like the injection to the pipeline and whatnot. So that's stuff that we won't go into now, but the gist of this plugin is we look for the module that we want to patch, which is fpm main.c. Then we look for the function where the bug was at, which is in request info. And in there, we're counting basic blocks. And at this point, I'll admit that this is kind of ugly. It turns out in the LVMIR, there is no unique identifier for a basic block, and there's no unique identifier for an instruction. So I cannot tell my plugin to go to instruction 526 and start working there. This is why I go counting through the basic blocks. This is also why this plugin will fail if the code base changes enough for the basic block offsets to be shifted, which is a different problem. There's a solution for that, and we'll talk about that in a minute, of course. But so for this proof of concept, I literally just counted down the basic blocks and said basic block 68 and basic block 71 is where the patches are at. And then simply what you do is you go to the end of the basic block, you move up by 2 instructions. So you don't want to fit, you don't want to hit the jump instruction, which is at the bottom of the basic block. You want to hit the compare instruction, which is above. And essentially what we're doing is we're nulling out that compare instruction. What you see there in the middle, and apologies at this point, there's no commentary in this code, is we create a new compare instruction which compares 1 and 1 with each other. So what you see there is we create the left-hand side of the compare instruction, the right-hand side, those are the items, and with this, we generate a compare. The dummy compare is the variable name, and iCompareInst is the new compare instruction. And we take that construct. This is how you build instructions in LVMIR. It's fantastic. With that construct, again, we go to the end of the basic block, and then we move up 2 instructions, which you see there with ins and minus minus. That's me moving up in the basic block. And then with replace inst with inst, we replace the old compare with the new compare. So that then compare will always be true, and that means that the check is voided. And that's wonderful. And then there's a modified variable that tells the compiler that we modified the code, which is important. All right, now you saw the code. Whoops. Now there's the next demo. Before I tell you how to do this smarter. Demo number 2. Praying to the demo god. Let this work. We go into the second. How much time do I have left? So I'm late. PHP. I will just not recompile this. Just trust me. I built this code. I downloaded the actual patched version, and then I compiled it and removed the patch. And now we're going to be launching the thing. Sudo launch. That's not good. I was kind of thinking that might happen because bash scripts. There's some ROI. Do it. Oh wait, we have an issue here, remember. I had panic. Alright. The demo guys are still with me. I just launched Nginx, and I launched it including the PHP FPM module. That's what we want, and that's the vulnerable part. The reason why launching this is kind of complicated is because I used Nginx in my last demo as well, so I have two different versions of Nginx up there, and I need to watch out which one to start. Okay, this should be the vulnerable version that's running. Now, here's the exploit. The exploit, as mentioned, I did not write this exploit. The credits for this go all to email learner, who originally found the bug and wrote the exploit, which is great. The server is running on my local host, which is handy, so now I'm kind of exploiting my own system. And that is at 27001. At port 80. And we want script.php. Now this should run, and then I'll need to kill the process. It runs. There are some error messages. The exploit works, but it also gives me some error messages, and I did not take the time to fix that problem. Apologies for the chaos on the screen, but now our server should be exploited, and now let's hope that this actually works out the way it should. So now if I run a wget on the address that I used with port 80, script.php, question mark, A equals the command that should run a who am I that gives us the results. Now, one thing I noticed is that the exploit is not super reliable, so I might need to run this a couple times. There was 0.
There.
Please. It doesn't actually give me any returns. That's a bummer. God damn it.
I think they bring this steps and also.
What was that?
See.
To the C1? Oh.
Champ. Yeah, right there. Child exited on single 6. Take a look.
That might be a problem. The demo does have left me a little bit over time. But I need to apologize at this point. The demo does not currently work, and I don't know why. I mean, I know why it failed. And that needs some fixing. Let me do this. I'll run the demo again tomorrow. I'll record it and I'll put it out on Twitter so that everybody can look at it. That might be the best solution at this point. Let me move on with my slides. So what I actually wanted you to see is, like, if I run this wget here with a command attached to the URL that I'm querying, that command will be run on the server as the user that the server is running at, like that Nginx and PHP are running at. And I'd like to point out again that I did not write that exploit. However, I did unpatch the FVM code. Well. Alright, that didn't work. I promise you it worked this morning, and I will record a video and I will upload it, and y'all will see the damn demo. Cool. And I promise you this could have been done smarter. There's the option to do Clang plugins. They're a lot more boring because in Clang you work on the AST and not on the LLVM IR. And I wanted to work on the IR, so that's why my plugin looks at an IR pass, not at a Clang interpretation. But you can do that too, and if you want to learn how, there's stacks of documentation about that too. Awesome. As mentioned, you can mod LLVM itself and actually put the pass that I ran as a plugin into the compiler. However, there's an issue with that. You need to rebuild the compiler, and if you want to backdoor someone else's compiler setup, you need to take the whole chain that you modded and put that on the target machine. As opposed to if you build a plugin, you just put the plugin binary onto that machine and change the build command to load the plugin at build time, which I think is the more elegant way to attack. But everybody there is an instruction on the slide, which I have from the link in the bottom, how to actually modify, like how to take your pass and build it into the LLVM toolchain. There's still issues with that, and I'll go through that very quickly. Of course, you need to build someone's build system first, which is the whole elegance of the SolarWinds attack. It's not that they changed the source code, like everybody can do that, but like that they breached the build system and plugged their own backdoor into that system and had it built into the update. That was the genius part about it. So again, modding the compiler and modifying what's built is not the difficult part. With great power comes great responsibility. If you modify something in the compiler, make sure that it doesn't actually break the binary. That's not a big problem if you just remove two instructions. But like, if you start changing multiple places and multiple situations, you might actually break the binary that comes out after. And that's a problem. Also, the LLVM and Clang API keep changing, which is wonderful. Their documentation isn't updated nearly as much as our code. It's kind of comical. So you read the documentation, then you read all the commands on GitHub where people comment of why the thing doesn't work anymore, and then you find out through the commands that the documentation wasn't updated. It's hilarious. Yeah. Lots of issues. Finally, what do you need to get started in this field? Do you need to know assembly? What kinda? Do you need to know C++? What kinda? Do you need to know compilers? Kinda. But you will have understood from this presentation that the whole subject is very approachable. So with some assembly background, with some C++, and with some compiler background, you can totally do this yourself. And please go out there and build more backdoors. They're awesome. Finally, I think of over time, but I have this beautiful slide that says any questions. So if I have any time, please ask me questions.
Great, folks. Are there any questions? I can come and run the mic. All right, Antonio, here you go.
Hi, thank you for your talk. I have a question about the entire toolchain and how would you manage the software version chaining, which is changing version, and how do you actually manage to rewrite your plugin of LLVM when the source code changes and you lose basically the retrocompatibility with your LLVM? Imagine the wonderful word you described, which is the exploit working, you can inject the entire chain in your target and they will compile this thing. Now the source code is not anymore compatible with your LLVM version because they are using some new quirks that the newer version of LLVM is actually offering you. So how would you actually keep yourself exploiting the remote host in case of remote update?
Where the complications come in. That's why I was saying, the real problem is not backdooring the compiler, but staying alive in the changing environment. For my proof of concept, it's easy because I control all variables, right? I control which version of LLVM I'm using, and I can test the thing, and I can look at the output, and I can verify it works. If you're really targeting someone else's build chain and you're in there, you need to live by their changing environment. So if they update the compiler, you better be on it to update your attack before they find out that your plugin is failing in the build chain. And that is where the tricky part comes in. Honestly, I don't know a solution for that. I'm not into breaking other people's build chains. Not yet, anyway. But so an interesting issue that I found with the change in compiler versions is that as the APIs change, the plugins need to be updated because their APIs are not the same anymore. A big change that they did in the last 2 versions or how far it was ago is the pass managers. And if you've worked with LLVM, you'll know that there's the legacy pass manager and then there's the new pass manager. And that was a big change. They communicated it, but in my opinion, that was a bigger change than they let people know about. And that was a bit surprising. I haven't worked with... Yeah. But so the refreshing part there is that GCC doesn't talk about their changes at all. You will not find documentation about how to write plugins. You will not find documentation about their APIs. All you know is reading through the source code. I actually appreciate that LLVM They do have blog posts. They do have announcements. They do want people to use their infrastructure, and that's refreshing. Yeah.
Right, folks. Well, thank you, Marion, for a lovely talk. Thank you for kicking off the bootloader evening.